Hi everyone, this is a joint work with Brett Valiant about proving stronger calibration lower bound using a new technique called sidestepping. Our research is motivated by this example, which is a typical example for online learning and online predictions. So in this weather forecast example, we are predicting a sequence of binary outcomes, like whether it will rain or not tomorrow, and the predictions being made are fractional values between 0% and 100%. So this begs the question, to what extent these numbers can be meaningfully interpreted as probabilities of raining. We formulate this as a simple binary prediction setting, which is a multi-stage game between a forecaster and the nature, which we also call the adversary. The game consists of capital T steps. In each step, little t, the adversary picks some binary outcome B of t that is either 0 or 1. At the same time, the forecaster makes a prediction P of t that is a real number between 0 and 1. And it's crucial that both actions happen at the same time, so that they cannot depend on the action of the other player in this round. But both actions can depend on the history of the previous t-1 time steps. So in other words, both the forecaster and the nature are adaptive. So we can paraphrase our question as follows. To what extent this prediction value P of t can be interpreted as a real probability that the outcome B of t is 1. A natural attempt is to define some notion of prediction loss as a performance metric for the forecaster. So for example, let's take the distance between B of t and P of t, which are the outcome and the prediction at the time step t, and sum over all the capital T time steps. We will say that the predictions are meaningful probabilities only if this loss is low. And one issue with this is that when the loss is very high, we don't know whether it's because the outcomes are inherently noisy or because the predictions are bad. So one extreme example is that all the binary outcomes B1 to B capital T are independent coin flips of a fair coin. And we can verify that no matter how we choose P of t, the expected loss defined as above is always t over 2. So in this definition, all predictions are equally bad or equally good. But intuitively, the best predictions should be 1/2 at every single time step. So to justify this intuition, let's take the thought experiment. Suppose that all the predictions P1 through PT are 1/2. So intuitively, this means that all the actual outcomes B1 through BT should resemble the flips of a fair coin. And in particular, the sum of those T bits should be roughly T over 2 by the large numbers. And more generally, suppose that some value P star is predicted at n different time steps, T1 through Tn. We also expect that those n outcomes should be Bernoulli samples with parameter P star, and in particular, the sum of those n bits should be roughly n times P star. And this notion is known as calibration, and here we're using it as a minimal requirement for the predictions to be interpretable as meaningful probabilities. This notion of calibration dates back to at least the 1950s, when Breyer suggested in the literature of meteorology that a weather forecast should be evaluated by comparing the probabilities being predicted and the actual frequency of the event of interest. And this notion has been adopted for online prediction and online learning since the last century, and it has gained more focus from both the machine learning community and the algorithmic fairness community very recently. Let's go back to our prediction setting. We can naturally define this quantification of calibration criteria, which we call the calibration error. So n of p denotes the number of times that value p is predicted by the forecaster throughout the first capital T time steps. And m of p denotes the number of positive outcomes among those n of p time steps where p is predicted. So this ratio, mp over mp, is the frequency of positive outcomes, conditioning on that p is predicted. And we're taking the difference between this frequency and this actual prediction value P, and we weight it by the number of occurrences of P. And equivalently, this definition can be written by taking this NP inside the absolute value as this summation. So each term, this NP is the actual number of positive outcomes, while this P times NP is the expected number of positive outcomes, assuming that all those outcomes are Bernoulli samples. And we call this difference as the bias associated with prediction value P. And this definition coincides with the L1 calibration error in the machine learning literature up to a factor of T. And the question we study in this book is what is the min-max value of this calibration error? In other words, suppose that the adversary is trying to maximize this error, where the forecaster is trying to minimize it. What is the scaling of this calibration error as a function of T? This problem was first studied by Foster and Walker in 1998, and they proved a positive result, stating that some randomized forecaster achieves a calibration error of roughly T to the 2/3, and this holds for worst case and adversarial adversary, and even if the adversary is adaptive. And on the lower bound side, there's a folklore result stating that the error cannot be lower than root T in the worst case. And this can be simply proven by considering the case where the outcomes are flips of a fair coin. And in this scenario, the intuitively biased predictions are 1/2 at every time step. And then the calibration error reduces to this expectation, which is a binomial random variable and its expectation T/2, and this is known to be scaling as root T. And in this work, we prove a non-trivial lower bound that is scales as T to the 0.528, which is the first root T lower bound, and first super root T lower bound for this problem to the best of our knowledge. And we don't expect that this 0.528 is the right exponent for this problem, but we do hope that many of our techniques for proving this result will be useful for closing this gap between upper and lower bounds, and maybe even for more general settings that involves calibration. So before going to our results, let me describe one obstacle to proving lower bounds on this setting. So in many online prediction or online learning settings, one nice thing about the error metric is that the error is not decreasing over time, meaning that once you make a mistake in the past, you cannot correct that mistake in the future. But this is not the case for the calibration setting, and the forecaster can act strategically to cancel out some of its previous loss and cover up some of its previous mistakes. Let's see one example for this to happen. Suppose that the time horizon is divided into 3 blocks. In the first block, the outcomes are random bits. In the second block are all ones, and the last one are all ones. The second one are all zeros. And what a truthful forecaster will do is to predict 1/2 on this black block, and 0 on the second red block, and 1 on the last block. And according to our calculation on the last slide, the calibration error is roughly root T. But a strategic forecaster can do some different things. It may still predict 1/2 on the first black block, but then it can drive its error down to 0 using the future bits. For example, suppose that the number of ones is greater than the number of zeros by 10 on the first black block. The strategic forecaster can predict 1/2 for 10 more times on this red block, so that the number of ones and number of zeros are even, and by definition, the calibration error will be 0. And this cover-up scenario is also called backcasting by Foster and Hart. The idea is that the forecaster is using the future bits to make its previous predictions look nicer, so it's not really forecasting. So to overcome this cover-up obstacle, we will take a detour and define a different game, which we call the sidestepping game. In this sidestepping game, the game state consists of k cells arranged in a row, and let's number them from 1 to k from left to right. At the very beginning, all those K cells are empty. And in each round of the game, the adversary will act first. He picks an empty cell between 1 and K. So in this game configuration, the adversary may pick either cell 1 or cell 3. Let's say it picks cell 1. And then, after knowing the cell J being chosen by the adversary, the forecaster will place an arrow pointing left or right into that chosen cell J. So let's say a right arrow is placed. And after that, any arrow that is placed earlier that are pointing to this cell J will be removed. So in this configuration, only the arrows in cell 2 and cell 4 are removed because they are pointing leftwards towards cell 1. And the right-hand side, the rightmost arrow will not be removed. So after this step, the configuration becomes this. The goal of the adversary is to maximize the number of arrows after a specified number of rounds. And it's a zero-sum game, so that the forecaster will minimize this number. So we can define some game value opt of KR as the outcome of a game with K cells and all rounds, assuming that both the adversary and the forecaster are optimal. Let's see one instantiation of this sidestepping game. Suppose we have 5 cells at the very beginning, and all those cells are empty. In the first round, the adversary will pick cell 3, and a right arrow is placed by the forecaster. In the second round, cell 2 is chosen, and a left arrow is placed. In the third round, cell 4 is chosen, right arrow placed, and the cell 3 becomes empty because the arrow is pointing rightwards towards cell 4. And in the last round, cell 3 is chosen again, and a right arrow is placed. So after 4 rounds, there are 3 remaining arrows in this instantiation. So let me describe at high level why this sidestepping game is relevant and how it connects to the prediction setting of our interest. So let's go back to our prediction setting, and we have this interval 0, 1, which is a space of all possible predictions to be made. And let's say at some point in this prediction scenario, we have this inequality. Let's recall that n of 1/2 is the number of times that 1/2 is predicted, and m of 1/2 is the number of positive outcomes among those time steps where 1/2 is predicted. So this inequality says that among the time steps where 1/2 is predicted, the fraction of ones, the fraction of positive outcomes, is actually greater than 1/2. Let's also recall that the calibration error contains a term that is the absolute value of this difference. So it's saying that the prediction value of 1/2 is contributing some bias towards this calibration error. Let's assume that the next prediction being made by the forecaster is still 1/2, and let's see what happens depending on what next bit is. Suppose that the next bit is 0, n will go up by 1, but m will not change, so that the difference goes down by 1/2. And as a result, the calibration error goes down by 1/2. And if the next bit is 1, both m of n will go up by 1. And because of this factor of 1/2, the difference goes up by only 1/2, and the calibration error goes up by 1/2. And more generally, suppose that the adversary picks the next bit according to the Bernoulli distribution with parameter p star. The expected increase in the calibration error will be p star minus 1/2. And because the adversary tries to maximize this error, the reasonable strategy is to pick some p star that is greater than 1/2. So we have this picture here. And this is analogous to the following picture in the sidestepping game. Let's say there's a left arrow in the cell in the middle. And the adversary, since trying to maximize the number of remaining arrows, it doesn't want the left arrow to be removed. So we'll pick some cell that is on the right-hand side of this left arrow. So we see some analogy between these two pictures. Roughly speaking, these cells in the sidestepping game are some discretization of this interval 0, 1. And in this game scenario, the left arrow roughly corresponds to the inequality on the upper picture. And the fact that the adversary tries to pick some cell on the right-hand side of the left arrow is analogous to the upper picture where the adversary tries to pick some P star on the right-hand side of 1/2. And more formally, we have our main result. Let's recall that opt of KR is the outcome of a game with K cells and R rounds, assuming that both players are playing optimally. We say that a pair of numbers alpha beta is admissible if it holds that opt of K and K to the alpha's power is lower bounded by K to the beta's power for all K. So every admissible pair specifies a sequence of lower bounds on this same value opt. The main theorem states the following: for every admissible pair alpha beta, there's a lower bound on the calibration error that scales as roughly t to the c's power, where c is a function of alpha beta as follows. And to prove some lower bound that is stronger than root t, we need c to be greater than 1/2. And this is equivalent to saying that beta is greater than alpha over 2. And also, the best lower bound we can prove from this theorem is t to the 3/5, assuming that 1/1 is an admissible pair. But we don't know whether it is true or not at this moment. Let me spend the rest of this talk for finding admissible pairs and to prove our claimed lower bound on the calibration error. We start with a simple fact stating that opt of 2 to the t minus 1 and t is exactly t. So there's a simple proof by binary search. That is, we look at all these cells at the very beginning. The adversary picks the cell in the middle, so that the number of cells on both sides will be 2 to the t minus 1's power minus 1. And depending on the direction of the arrow placed by the forecaster, we can recurse on either half of this state, so that every cell and every arrow placed in the cells are not removed by the later cells. And this proves that opt of k and log k scales as log k, but this is not sufficient because for getting admissible pairs, we want the lower bound to be roughly k to the beta's power for some positive beta. So we need another fact that allows us to construct larger lower bounds on opt based on one simple lower bound. So this fact states that if opt kr is lower bounded by c, the opt of k to the t's power and r to the t's power is also lower bounded by t's power of c plus 1 over 2. So without this factor of 2, it's stating that the right-hand side is roughly c to the t's power. So this fact is some composition property of this game value. Let's prove a very simple example, a very special case of this fact. We know that opt 3/2 is lower bounded by 2 because we can first choose the cell in the middle and then choose the cell that is not pointed by the arrow. And we are trying to derive from this fact the lower bound that opt 3 to the t's power and 2 to the t's power is lower bounded by 3/2 to the t's power. For simplicity, let's define capital T and M of t as the same value as 3 to the t's power and 2 to the t's power. So it is sufficient to show that M of t grows in a rate that is greater than 3/2. So let's start with the game state with this many cells. We can naturally divide it into 3 blocks. Each block has length 3 to the t's power. So in the first step, we can simulate the adversary on a game with 3 to the t's power cells and 2 to the t's power rounds. So we can spend the first 2 to t rounds in the block in the middle. And by definition of M of t, if the adversary is playing optimally, the number of surviving arrows will be at least M of t, denoted by the red arrows. And in step 2, and one observation is that among those empty surviving arrows, at least half of them will be at the same direction. And let's say the majority of the surviving arrows is pointing leftward. Then in step 2, we will play another 2 to t rounds in the block on the right. And we're still simulating the best strategy for the definition of empty. And after these 2 to t rounds, the number of surviving arrows on the right block will also be at least empty, and they are denoted by the green arrows. But also, part of the arrows surviving step 1 will get removed. And in this picture, they are exactly those pointing rightwards. So in the end, the number of surviving arrows will be at least empty over 2 plus empty. The first term comes from the leftward arrows after step 1, and the green term are those surviving arrows from step 2. So we prove our desired inequality that empty plus 1 is at least 3/2 times empty. So combining these two facts, we can derive a sequence of lower bounds on opt. And if we write the first argument of opt as k, the second argument and the right-hand side are also polynomials in k, and the exponents alpha and beta are just functions of t. So we get this lemma stating that for every integer t, we have an admissible pair alpha t and beta t with this definition. So we can plug this lemma back to our main theorem and get a sequence of lower bounds on the calibration error with different exponents ct, which is a function of alpha t and beta t. And by choosing the optimal value of t, we get our claimed lower bound with exponent 0.528. So in this talk, we have seen that the calibration notion is a very natural criteria for the binary predictor to making meaningful predictions. And we also saw that the calibration error is a natural quantification of this criteria of calibration. But unfortunately, if we use calibration error as a metric directly, the forecaster trying to minimize this error will cover up some of its mistakes, and this leads to unnatural behaviors from the forecaster. But fortunately, by proving a lower bound on this calibration error, we show that the forecaster cannot benefit too much from cover-ups, assuming that we consider the worst case behavior. And the best result along this line would be a matching lower bound of t to the 2/3 for this kind of prediction problem, because the upper bound of t to the 2/3 are achieved by some truthful forecaster that doesn't do these cover-ups. And if that were true, we will be able to claim that the forecaster cannot strictly benefit by covering ups. We also saw that the sidestepping game is a natural and useful abstraction for proving lower bounds for this prediction setting. And we hope that this technique will be useful for closing the gap between upper and lower bounds, and maybe even extending to more general settings that involve the notion of calibration. Thank you.